Hi everyone. My name's Sarah. As mentioned before, I'm a PhD student at UC Berkeley, working with Jan Stoika and Joey Gonzalez in the Sky Computing Lab. And previously, I've worked on systems machine learning and also systems for the cloud. And today, I'm here to talk to you guys about Skyplane and how you can quickly and cheaply share data both across cloud regions and also cloud providers. So just to provide a bit of motivation for why are we talking about this problem of sharing data across clouds. So basically, the situation that we're in today is that organizations and people and workloads are basically partitioned across cloud provider regions and services. So if you're an organization, it's very likely that you're trapped within one of these big three cloud providers. Maybe you also use Lambda Labs or another smaller cloud. And you're basically stuck within these providers and the services that they offer because of data gravity. And what I mean by this is that because it's difficult to move your data across both cloud regions and providers, it means that you're basically locked into whatever services or hardware resources that cloud provider offers you. So even if GCP has some better hardware, it can be really difficult to move all your data and your models and whatever other data that you might have if you're already locked into AWS. So let's go in a bit more about what this problem of data gravity really means. So first of all, there's this issue of slow transfers. So if you're moving data between two AWS regions, you might only get 21 megabits per second, which means that even just a 70 gigabyte data set, which is fairly small, will take about an hour to transfer. Another problem is expensive egress fees. So cloud providers actually charge per gigabyte egress fees, even just within their regions, about 1 to 2 cents, and then also charge very high egress fees, up to 23 cents, usually around 9 cents, whenever you want to transfer data out from that cloud provider. And so what this means is that to move that same 70 gigabyte data set is equivalent to running 34 M5X large instances for an hour. So these egress costs can really add up to be very comparable to the compute costs that you're also paying in the cloud. And lastly, there's this issue of painful integrations. Every single storage service has different ways of accessing data. This is a whole list of integrations that Airflow has. And these are all basically the interfaces for interacting with data and moving data across these providers is very annoying. So just to give an example, here's what it's like to transfer data between two regions in just AWS using the AWS CLI. Oops. Is there a way to get it to play? Oh, okay, that's too bad. Well, basically what it will do is it'll very slowly start transferring data at about 21 megabits per second. So yeah, and we'll show, there'll be another video, which I guess probably also won't play, but oh well. Okay, so what is Skyplane? So basically, we have this problem of moving data across regions and clouds is very slow and expensive. So if we have some kind of applications that might want to access data across clouds, like a data pipeline or some web application or maybe even a container registry, basically, each of these applications has to manage this very complex, slow, and expensive process of potentially moving data and sharing data across both multiple cloud regions and also cloud providers. So the vision with Skyplane is to basically have an inter-cloud broker for managing data across cloud providers. So instead of directly interfacing with the object stores or the transfer services that the cloud providers offer, each of these applications will instead interact with the Skyplane inter-cloud broker for data. And then that, in turn, will manage interfacing with each of the storage offerings of the clouds. So Skyplane works on both the transfer and the storage side of this. And we currently have a cross-cloud transfer broker, which basically offers a very similar API to the AWS tools, where you can basically do Skyplane CP between one object store URL path and then a destination, which can be one or multiple object store URL paths. And then we also have ongoing work in a cross-cloud storage broker, where we can basically allow users to interface with what appears to be a single object store URL, but is actually multiple storage services behind the scenes. So this talk is mostly going to focus on the transfer side of this. And Skyplane's inter-cloud broker actually allows for up to 110 times faster data transfer between major cloud providers. Also 3.8 times cheaper egress costs for transfers. And then finally is integrated with most public clouds and also on-prem. So a bit about this transfer broker. So the way this works is that we basically optimize cloud networking. So we take both unicast and multicast transfer. So unicast transfer is point-to-point replication. You might want to move 5 terabytes from AWS to GCP, versus a multicast transfer is one-to-many. So maybe you want to publish 300 gigabyte model weights to 10 different regions. So basically, Skyplane will take in these requests and then use a service catalog, which is basically a map of the cloud wide area network. And then it also uses a throughput grid and a price grid, which basically maps out what is the throughput of all these network edges in the clouds, and then also what are the pricing, basically all the egress pricing of different regions. And it passes all this information along with the transfer request into the Skyplane optimizer. So the optimizer will basically figure out how can I construct a network, an overlay network, to transfer data in a way such that the cost is minimized and also the throughput is maximized. And then finally, once we have this plan, we execute this over the Skyplane overlay network, which can work on top of multiple different cloud providers. So we currently have Cloudflare, AWS, Google Cloud, Azure, IBM, and also on-premise. So the Skyplane overlay network, just to describe this a bit more for people who aren't familiar, is basically we create virtual machines across different clouds that sort of act like routers in each cloud to basically read from the object stores in the source and destination, or in the source regions, and then relay this information to VMs in the destination clouds, and then write to the object stores there. And so this whole network for executing the transfer is actually doesn't require any cooperation from the clouds because it's using public APIs that run inside of your cloud VPC. So Skyplane will actually take in your cloud credentials and then execute on your behalf all these resource requests so that we can execute the transfer. So you don't have to trust any kind of like Skyplane service or anything like that, and everything's all open source as well. So this is the other video that's not going to play. It'll play? Oh, okay, great. So this one's the more important one, so it's good that this one's playing. So yeah, this is what transferring data with Skyplane will look like. So you can see it's a very similar command like Skyplane copy between 2 S3 paths. And so you can see here that it's basically creating a bunch of virtual machines. So it's trying to here create 8 virtual machines, and then installing the Skyplane gateway package so that these machines can basically execute the transfer. And then now you can see that it's launched a 70 gigabyte replication job, and it's actually now transferring this data at almost about 20 to 30 gigabits per second, which is much, much faster than the 25 megabits per second that we would have seen before. And so we can now see that a transfer that otherwise would have taken an hour to complete now takes just 16 seconds. So I'm going to get a little bit more into, I guess, the research side of this and how we actually achieve these faster and cheaper transfers. So let's consider an example where, that's a picture of me. I'm transferring from some cloud in some region on the East Coast to my collaborator Paras, who's on the West Coast and perhaps on a different cloud. And so why are these transfers slow and expensive, and what can we do about that? So first, one issue is that there's congestion along the direct path. So maybe this path is really popular, and there's not enough bandwidth by the cloud allocated, and so then this makes the connection really slow. Another potential issue is poor peering between providers. So AWS and GCP aren't exactly too concerned about if data can transfer really quickly in between them. So this is oftentimes this networking is not very optimized. And then finally, there's also packet loss from the physical layer. If you're transferring data across long distances, there'll inevitably be some packet loss, and this can also result in just having slower transfers. So there's a couple of techniques that we use to sort of alleviate this problem, and I'll go through them one by one. So one is overlay routing, which we use to circumvent slow or expensive links. So you can see this example up here is we're transferring from an Azure UAE North region to North Virginia region in AWS. And the direct path is pretty slow, relatively speaking. It's only 1.8 gigabits per second if you use 2 VMs in each region. So we can actually get around this path and instead go through the Mumbai region in AWS. And if we take this indirect path, we actually are able to get 4.6 gigabits per second. So this is kind of odd because it means that you're basically sort of taking a longer path, but because each path has higher throughput, you actually are able to transfer more quickly by using this indirect path. So our solver will discover these indirect paths using profiled throughput across all cloud region pairs. So even though there's a lot of different possible options for the routing, we have written a solver that can pretty quickly determine the best routing given two different source and destination pairs and the size of the data. So this is the first technique, overlay routing, basically using indirect paths to avoid slow and expensive links. The second technique that we use is parallel VMs. So cloud providers actually limit the egress and ingress limits for their virtual machines. So you can actually see with AWS, you can't get, for a single VM or of this type, you can't get more than 5 gigabits per second, regardless of whether you're transferring data within or across clouds. Azure is more generous. You'll have quite a bit more bandwidth, up to 15 gigabits per second, both for inter and intra-cloud, but there can be a lot of variance. And then GCP, on the other hand, is pretty generous with intra-cloud bandwidth, but for inter-cloud bandwidth, they'll again cap you at 5 gigabits per second. So this is a big part of the reason why transferring data between clouds is really slow, because the cloud providers will actually sort of explicitly limit you from being able to transfer at a faster rate. So yeah, basically clouds throttle these egress speeds. So we can get around this by basically using more VMs. So if you can only get 5 gigabits per second for a VM, you can allocate 10 VMs using cloud elasticity and then basically get 50 gigabits per second. So this is another technique we use. And then finally, we also use parallel TCP connections. So we can basically parallelize the connections between each pair of VMs. And then we also use network tiering and compression to basically reduce the cost of the transfer. So all of these techniques are described in more detail in our NSDI 2023 paper, which you can check out at, you can probably just Google it or go to this link. So the second part of this talk, I'm actually going to talk a little bit about Sky storage and data replication to multiple destinations. So all the techniques I've been talking about so far have been just a single destination. How do we basically do like a unicast transfer? So to motivate, like, why do we then want to transfer to multiple destinations? Well, so there's this issue of how do you make data accessible across regions and providers in the cloud. So in cases where you might want to do geo-distributed model serving, maybe cross-organization data sharing, or just any cross-cloud application, you often want to make maybe some data that's currently in AWS accessible across multiple other regions and also provider destinations. But of course, accessing this data directly from each cloud can be very expensive and slow, and every single time you maybe try to access some S3 data from Google, you're going to incur a high latency and also that egress cost that we talked about before. So for repeatedly accessed data, we basically want to make sure that the data is sort of pre-replicated in order to minimize the access latency and then also the overall egress cost. So what this means is that basically, if we want data to be accessible in many different places, we probably want to replicate that data ahead of time from the source region to wherever else we might want to access it. So this might be many different regions around the world and also across many different cloud providers. And the sort of most basic way that we could do this is that we could just directly replicate the data. So whenever something's written to the source region, we then directly copy it to wherever else we might want to be accessing the data. But so there's a couple problems with this. So one is, again, it's very expensive. We're going to have the same problem as we did with the unicast transfers, where some edges will just be very expensive. And then also we have this issue of limited source egress. So again, clouds will throttle egress limits on VMs. And so here, if we're transferring out like 10 copies of the data, then that source is going to be a huge bottleneck. And then finally, again, we'll have low throughput connections, so we want to avoid these, similar to the unicast case. So the question here is, how can we basically publish data to multiple clouds and regions in a way that's both fast, so high throughput, and also cost effective, so low network costs? So a bit of a more, I guess, mathematical representation of this is shown here. So if, say, we're trying to transfer data from GCP in North America to a couple different Azure and GCP and AWS regions. So the cost breakdown of this is that this ends up being 90 cents per gigabyte, or even $900 per terabyte to just replicate data once to all these different regions, just because we're transferring across so many different regions. So we can actually optimize this cost by revisiting our intro algorithms course material, which is using a minimum spanning tree. So we can basically apply the minimum spanning tree algorithm onto the graph of costs to build a cost minimizing tree, as you can see here. So this will actually reduce the cost by about 30% down to 60 cents per gigabyte. And we can go further by using something called a Steiner tree, which will also consider non-destination nodes. So these are also called overlay nodes. So Azure Canada Central and AWS US West 2, neither of them are places where we need the data to go, but it turns out that transferring the data through those regions actually reduces the overall cost. So this Steiner tree will actually reduce the cost almost 50%. So then we get like about 48 cents per gigabyte. But the problem with this is that this will actually hurt our throughput significantly as compared to the other distribution trees I was showing. So the question is, how can we sort of jointly minimize costs while also making sure that we can meet some kind of minimum throughput SLO? So again, the way we do this is we define an integer linear program which optimizes the replication costs given some time budget that we're given. And this ILP will basically determine what should the topology or the structure of the replication graph look like, how many VMs should be created in each region, and then also what data should be transferred across what paths. So if you use this, you actually get this like crazy looking graph, which is transferring from the red to the green and using a bunch of overlay regions and also transferring different subpartitions of the data, which are labeled 1 through 10, across different paths. So this might look really inefficient, but it actually gets 6 times the throughput and also a 45% cost reduction as compared to the direct replication topology that I originally showed. So this is kind of a graph showing all the different ways that you can construct your replication tree. So the direct method is of course terrible, it's extremely expensive and slow. There's a couple other baseline algorithms we also implemented since this was for the paper. But you can see this line in purple is actually the Pareto curve that we basically get for the cost throughput trade-off, where we can put in different replication time budgets. So basically, if you don't really care how long the replication time takes, then you can get a very slow but very low cost solution, versus if you care a lot more about the replication time, then you can put in a tighter budget and get slightly higher costs, but still really good throughput. So overall, we get about a 5x replication speedup and 53% cost savings for direct transfers. Though this will, of course, vary depending on what your source and destination regions are. This was another comparison we did to the S3 multi-bucket replication. So S3 offers a service where they'll basically automatically replicate data that you write to one region to other regions. So this, of course, doesn't work across clouds, but we tested this just against like within AWS regions. And we found that by having more intelligent replication trees, we could get up to 2.3 times replication speedup and 61% cost savings. So one other thing I wanted to mention is the impact of incumbent clouds. So I'm sure as some of you know, there's new cloud providers like Cloudflare, which are actually offering free egress. So how does this actually impact their solutions? Because all the cloud providers I've talked about so far charge these very high egregious egress costs. So this actually results in a sort of neat solution where if you're broadcasting data to multiple clouds, you can actually route through free egress clouds to sort of, I guess, hack the costs in a way. So if you're transferring from Azure to maybe one AWS and one GCP region, you can actually transfer the data just once to Cloudflare and then use Cloudflare's free egress to broadcast out from there. So this will actually reduce your overall cost. And so I guess to summarize, Skyplane is an open source project. The storage stuff was still in progress, so not released yet, but all the transfer stuff that I talked about today, both for one-to-one transfers and one-to-many transfers, are all open source. You can use it both through a CLI tool and then also a Python API, and you can install it with pip install. We have an open source project. Everything I talked about here is open source. We've had a lot of positive community feedback about the project, and there's also multiple organizations that are currently using Skyplane today to transfer data between clouds and regions. And we're approaching about a petabyte of data transferred from people outside of our lab. So yeah, to summarize, Skyplane is an intercloud broker for data-intensive applications. We solved the problem of expensive cross-cloud transfers and slow cross-cloud transfers, and you can install it today with pip install Skyplane. Thank you. Yeah, are there any questions? Yeah? Yeah, so the question was, does Skyplane handle chunking the data to send the data across different paths? So yeah, the answer is yes. For the multicast transfers, basically in the planning stage, if we know that the data size is like 100 gigabytes, we'll basically we'll map each object store key to a subset of smaller chunks, and then we'll assign each of the chunks like basically a partition ID, which identifies like which path along the network should they take. So each of the VMs will basically look at a chunk's partition ID and then know how to route that data. Yeah? Yeah, so we're still working on the between two data centers. It shouldn't be too hard to adapt it to multi data centers because you basically have to run the Skyplane gateway Docker container in from between wherever you want to transfer the data, and then they can sort of communicate with each other. Right now, our on-prem support is unfortunately limited to just doing your local machine to the cloud and vice versa. Yeah. Yeah, so the question was, what use cases are we seeing people using Skyplane for? So one that I saw recently was there's someone who I think was using Google Analytics for their I think their marketplace website, but then they wanted to process the data inside of AWS. And so what they were using Skyplane for is, I think Google Analytics, they either don't make it easy or they don't allow you to export data into S3. So what they were doing is that they would export their data into BigQuery, or I think it was Google Cloud Storage, and then from Google Cloud Storage use Skyplane to synchronize that data with AWS so that they could access that data in AWS. I think other applications we're seeing is obviously there's like the GPU shortage. So that's like another workload where you might want to access training data or model weights across many different cloud providers and regions. Mm-hmm. Mm-hmm. Yeah, so the costs actually very rarely change. I think Google might have recently updated some of their costs, but it changes infrequently enough that we basically just have something to scrape all the costs whenever they're updated, and then we just basically, if you download Skyplane or look at the repo, you'll see like a cost.csv file, and it uses that CSV file basically to map out all the costs. Yeah, so the question was if the costs are only retail costs. So yeah, I do know that some people they have like special deals with cloud providers. So I think if that's your use case for your company, then what you can do is you can basically modify the costs, because it's all open source, modify the cost CSV to whatever pricing that you're getting. Yeah, over there. Yeah, so the question was, do the VMs auto and deprovision? So yeah, Skyplane will, at the end of the transfer, will tear down, or if there's a transfer error, we'll tear down all the VMs. And just as an extra safety precaution, we also make sure that the instances terminate after 15 minutes of inactivity. And that's a parameter that you can set in the configuration.
What about security? How do you deal with the credentials?
Yeah, so the question was security and how do we deal with the credentials? So there's the Skyplane init command, which you can see there, and then that will basically ask you to put in your AWS and other GCP credentials. And then once you enter those are all just saved locally, so they don't get like sent anywhere. And the credentials are then used to basically spin up the VM instances, because we have to have those credentials to create the VMs in your account. But other than that, they don't all of that happens on your local machine. And another security measure that we take is like all the VMs are created inside of cloud VPCs as a security measure. And then whenever data is transferred across VMs, we actually encrypt the data. So when the data is downloaded at the source VM, it's encrypted, and then right before it gets uploaded to the object store, it gets decrypted. So whenever the data is actually moving across the internet and moving across the VPCs in the clouds, it's all encrypted.
One more question? All right. Thank you.
All right, yeah, thank you, everyone.